What is the current status of solar energy? This video lecture is an updated lecture as developments in the PV world are unprecedented at the moment. This video lecture therefore is recorded on February 8th in 2018. First, I would like to discuss the growth of the cumulative installed photovoltaic power. The horizontal axis in this graph represents time expressed in years. We express the global installed power in gigawatt peak. In this course, we will discuss in great detail the definition of gigawatt peak. Total installed PV power is increasing exponentially. Last year, in 2017, the total installed power has surpassed the 400 gigawatt peak border. The moment that we exceed the 1 terawatt peak scale is in sight. The red bars indicate the worldwide annual solar cell production. The red vertical axis represents the annual production. As you can see, the annual production capacity had an exponential increase as well. Last year, a production capacity close to 100 gigawatt peak has been established. This is equal to 25% of the current cumulative installed capacity. So every year, 25% of the total installed capacity is being added. The annual relative increase in production capacity in reference to the previous year increased by more than 40% every year, which is again an unprecedented growth. In this graph, I only show how the various PV technologies contribute to the total annual global module production. The green and yellow colors represent the crystalline silicon PV technology. As you can see, the crystalline silicon PV technology is the dominant technology and contributes to around 90% of the total module production in 2017. This PV technology and the difference between monocrystalline silicon and the multicrystalline silicon technology will be explained in week 4. The pink color in the graph corresponds to the inorganic thin film PV technologies like amorphous silicon, cadmium telluride and CIGS. These thin film PV technologies are responsible for the remaining few percent and will be discussed in week 5 of this course. The next graph shows again the worldwide cumulative installed PV power. Now the different colors reflect the different regions in the world. The orange color corresponds to Asia, the green color to Europe, the blue area reflects the PV capacity installed in North and South America, and yellow corresponds to the Middle East and Africa. The Asian region has currently the largest amount of PV power installed. The main drivers for this increase are the regions in China and Japan. China has shown an unprecedented increase in the installed PV capacity from 2010 to 2017. The green area corresponds to Europe. The graph shows that up to 2012, the far majority of PV systems were installed in Europe. Now, Europe is the region with the second most PV power installed. However, the growth rate, as you can see, of the PV installation is significantly smaller in reference to the Asia and the Americas, which is corresponding to the blue-colored area in this graph. In the early years of this millennium, due to the introduction of various subsidies policies in Germany, Spain and Italy, the European market share increased up to 80% by the year 2008. Around this time, the PV market appeared to be a local European affair. From 2009, the domestic PV market in China, the Americas and Asia Pacific, mainly Japan, have started to increase very rapidly as well. So the markets in the other regions are catching up quickly. It is important to note that the total installed solar power has passed the 400 gigawatt mark in 2017. This is a factor 4 more than 4 years ago when I recorded this video lecture in the Solar Energy MOOC for the first time. An interesting aspect of the PV technology is that it is not only a European and American affair as 10 or 20 years ago. The local demand and the supply has been changing rapidly in the last 13 years. The next graph shows that the dominant market region does not have to be the region in which the PV modules are dominantly produced. On the vertical axis, the relatively market share is given. This figure illustrates the evolution of the worldwide supply or production of the PV modules in the various regions around the world. Gray represents Europe, orange represents China and Taiwan, purple the Americas, mainly the United States, and yellow represents Japan. Over 20 years ago, US was the largest producer of PV modules, followed by Japan and Europe. The share in module production of the US has been decreasing over the last 20 years. In the early years of this millennium, the share of Europe and mainly Japan has increased rapidly. The maximum share of Japan has peaked just above 40% in 2004. In the last 10 years, China and Taiwan have shown an unprecedented growth in PV module production. This revolution has been made possible by huge investment of the Chinese government into scaling up PV module manufacturing in China. China and Taiwan are currently responsible for 80% of the global PV module production. In 2000, the PV market was an essential local market mix. The local demand and supply in Asia, Americas and Europe were more or less in balance. By 2012, no local balance between supply and demand existed anymore. The majority of the demand was in Europe, whereas the majority of the production was in China. You see that the PV market has transformed from a local market of demand and supply to a global market of demand and supply. However, the local market in China is growing very rapidly in the last years and is currently the biggest PV market in the world. Another aspect that controls demand is the cost price of PV technology. How does the cost price of electricity generated by a PV system compare to the electricity delivered by your electricity energy company? To answer this, we have to look towards the learning curves. The learning curve is the graph which shows how the cost price, or in this case the sale price, is dropping in time. In time, the industry gets more experience. Progress in technology provides for better PV modules with higher efficiencies. This experience results in better and faster processing, leading to higher production yields. Upscaling of production leads to lower cost of the source materials. Bigger markets results in more and cheaper available finances and investments to guarantee further upscaling of production. Learning curves usually show an exponentially decreasing cost price in time until the technology or product is fully developed. In this graph, we have the average global sale prices of a PV module versus the cumulative installed power up to 350 gigawatt, which means that this was established around mid-2017. Important to note is that the sales prices, discounting some fluctuations, follow a largely exponential decay. Currently, the average retail price of PV module is below 0.4 euros per watt peak. Now we will see how the cost price of a PV system is not only determined by the module. The red dots show the decrease in cost price of a complete PV system. As you can see, in the early days of the PV technology, the system price was dominated by the module price. However, in the current situation, the contribution of the non-modular components start to play the most dominant role. With non-modular components, I refer to components like the racking, wiring, inverter, battery for standalone system, or even maintenance cost. The difference between the red and the green line corresponds to the non-modular cost and are indicated by the dark blue markers. This shows the learning curve of the non-modular components, which is dropping not as fast as the module price. This means that nowadays the reduction in the cost price of a PV system will be mainly limited by the cost price of the non-modular components. This shows the advantage of the crystalline silicon PV technology, which has a higher module efficiency ranging from 16 to 20% in reference to the thin film PV technologies. Higher conversion efficiencies means higher yields per area. While the non-modular costs per area are the same, the cost price per watt peak of the non-modular cost will be consequently lower for modules with higher conversion efficiencies. In block 1.2, we have discussed that hydropower is responsible for approximately 19% of the total worldwide electricity production, and nuclear is 16%. The question now is, how do these numbers compare to solar? For that, I have constructed the following figure. On the vertical axis, you see the cumulative installed nominal capacity, which is expressed in gigawatts of power. Note that this is a logarithmic scale. On the vertical axis, time is plotted expressed in years. Here we only consider the energy sources which are not based on fossil fuels. Orange represents hydroelectricity, dark green represents nuclear, blue represents wind, and red represents solar. The black line is the primary energy demand of the last 30 years and the forecasted energy for the upcoming 20 years according to the International Energy Agency. The installed nuclear power is hardly growing anymore, whereas the installed hydropower is still slightly growing in time. Wind is growing at a relative rate of 20% per year. As you can see from 2000, solar is the fastest relatively growing energy technology with a rate far above 40% per year. However, it's not fair to compare the installed nominal power between technologies like this. The numbers given here represent the maximum power the energy source can produce, but is not the average power the electricity source has delivered in reality. The relation between those two is called the capacity factor, which is basically a measure of how often an electric generator runs for a specific period of time. Nuclear has with 90% the highest capacity factor, followed by hydropower with an average capacity factor of around 40%. For wind energy, I have assumed an average capacity factor of around 30%, and for solar, I have assumed a capacity factor of 15%, which equals average of 3.6 sun hours per day, which is, to my opinion, an underestimation. A low capacity factor for PV systems can be explained by the fact that for most geographical locations, almost half of the solar day is devoid of solar radiation at night. If we use these capacity factors, we can look at the effective installed power for these electricity sources. Currently, solar energy generates a factor 8 to 10 less electricity than hydro and nuclear do. However, I claim that the trend in the growth of solar energy will continue the coming years. Currently, PV produces close to 2% of the world's electricity, and this share is increasing fast. If we bluntly extrapolate the trend of the last decade, we see that the installed power of solar energy will exceed nuclear, wind, and hydropower by the early 20s. It is just a matter of time that solar becomes the most important energy source not based on burning fossil fuels. However, the question is whether we can just bluntly extrapolate these trends. Let's do this for PV electricity. Extrapolation of the exponential growth would mean that before 2040, we would be able to produce the same amount of solar electricity as total primary energy demand required. But will exponential growth continue, or are there other forces at play? As discussed earlier, the current exponential growth of PV means that the annual installed production capacity of modules is 25% of the cumulative installed PV power in the world. This would mean that at the point that PV would meet the primary energy demand, the total production capacity would be redundant for the coming year. The investment in the last year's production capacity would not be earned back anymore. Therefore, a continuous exponential growth would for this reason not be a sustainable and cost-effective solution. When will the exponential growth slow down? This is, to my opinion, determined by the PV replacement market. In equilibrium, you produce just as much PV systems as are required to replace the PV systems that have to retire due to underperformance, outdated electricity yields in reference to new technologies, or are malfunctions or simply broken. For economic reasons, the annual production capacity can therefore not exceed the market of replacement. This market is equal to the total installed capacity of solar electricity divided by the lifetime of a PV system or solar panel. Let's assume a lifetime of the PV system of 25 years and that the final PV market would contribute to the total primary energy market with 10%. This means that with the current exponential growth of production capacity, we would reach a sustainable global production capacity by 2024. After 2024, the total installed cumulative PV power would enter a linear growth regime. Let's assume that the final PV market would contribute to the total energy market with 25%. We would reach a global production capacity by 2027 to achieve this objective in an economic sustainable manner. Let's assume that the final PV market would contribute to the total energy market with 50% and 100%. We would reach constant global production capacity by 2030 or 2032 respectively. This is most probably much sooner than you intuitively would expect. Why can solar currently guarantee a much faster capacity growth than the other technologies? First, solar energy is everywhere and available in great abundance. Realize that the total amount of energy in solar light incident on planet Earth is 10,000 times larger than our total energy consumption. By evaporation of water due to solar heat, hydroelectricity is a secondary form of solar energy. By solar-induced temperature difference, wind is a secondary form of solar energy. Consequently, solar energy is the biggest renewable energy source around. Secondly, hydro, nuclear and wind are centralized electricity generation concepts. It means that you need a big dam, big nuclear plant or wind park to generate electricity. Building these large systems requires governmental involvements and big investors. PV systems can be installed centralized in large solar farms too. However, the unique advantage here is that PV system can be installed decentralized as well. Many consumers of electricity can put their own PV systems on their home. They become their own energy producer independent of the market. Another important factor is that in most parts of the world, the cost price of PV systems have met or dropped below grid parity. This means that having your own PV system is cheaper than buying the electricity from the grid. In locations in which people do not have access to electricity, an autonomous PV system is the only solution and the cheapest solution. But even the large-scale utility PV demonstrates some unique forces. In several countries in the world, solar farms are being constructed that are going to deliver electricity for cost prices that cannot be realized using conventional fossil fuels-based plants. The current record today is a solar farm in Mexico. They will deliver in the near future solar electricity for $1.7 per kilowatt hour. Amazing. Both the installations of the decentralized and centralized PV systems will be a big force behind the solar revolution of the coming years and will change the energy landscape much faster than most people think, as shown in this graph. As more and more people become aware of the cheapness and availability of solar electricity, it's more likely that the growth will be further enhanced than it will be slowed down. In this course, I will introduce you to the technology behind this revolution. Therefore, I see you back in the next video.